Okay, any general questions? Today's big exam 3. I would say this one is probably going to be monumental compared to the other two, just because of how much reactions we have now covered and applied the concepts we learned in the first 2 exams. Okay, so are there any questions though? Last minute, just things you might want to just get a clarification on, or anything like that?
I was asking Catherine just before you didn't hear about when you have an epoxide.
Yeah.
In acidic conditions or basic conditions.
Right.
So it attacks a different place, right?
Yes. Right.
Okay. And then so if it's acidic, it attacks in more.
Yeah. So just think tertiary position, or more substituted. You're going to go. It's going to be acidic conditions will favor that side, and then you have something basic. So like an oxygen, negatively charged oxygen. Okay, and if there's no acid present, that will be the least hindered side. And this applies to any basic nucleophile. Amines, neutral amines, charged amines, charged sulfur, neutral sulfur, etc. Okay, so neutral nucleophiles or charged, basic conditions, because there's no acid being added in the same step, right? But if it's acidic conditions, you're going to have a strong acid as well as a weakly neutral nucleophile like water or an alcohol. Yeah.
Thank you.
Yep. Okay. All right. So last time we were covering alkenes. So let's just do a few more examples. But first I want to kind of just show you, if you have an iPad, there's this really neat app. It's called KingDraw HD. And you can pretty much draw anything. Okay, but I guess I use my maximum number of entries. All right, so if you know what ChemDraw is, it's a pretty useful software. All right, so this is available on the App Store. Great for iPad. So if you prefer drawing your iPad, you can even visualize these things in 3D. So pretty cool. I think it'll be a helpful resource. I'm sorry I didn't discover this sooner, but it's pretty cool, and it's free, so that's pretty awesome. Because ChemDraw, it's a single subscription, $1,000 per year. Okay, so the fact that this is a Chinese app, the Chinese are making it free, and it'll probably be a paid model eventually, but hopefully not as much as ChemDraw. All right, so I think it'll be pretty useful. The only problem with this is it's really hard to rotate, in my opinion. I guess it's okay right now, but if you kind of stop it auto-rotating, it becomes really cumbersome to rotate. So that's my only critique of that. Okay, so very useful. You can even generate nomenclature here. Okay, let's see if there's nomenclature somewhere. Yeah, so some properties. So yeah, you can do a lot of stuff with this. So I encourage everyone to kind of explore that. Okay, and you can even draw change pretty easily. So pretty neat. So if that interests you, it's called KingDraw HD on the App Store. And there's 2 versions. HD is for iPad. The non-HD one is for iPhone. It kind of works on the iPad. The Windows is just a little bit smaller, but it still works. All right, I'll just share that with you. Okay, so that's KingDraw HD. All right, so I wanted to bring our attention back to the mechanism we visited last time, because I feel like there may be still some misconceptions about the mechanism. So let's look at this 3D drawing here, okay? So this website, I referenced it on Canvas, CamTube 3D. You can see all kinds of mechanisms in real time, simulated, okay? So remember the first step? We have our alkene here. So what's the first step that happened when we have an alkene reacting with Br2?
The bromine splits.
Yeah, so the bromine is going to kind of approach perpendicular to the axis of the alkene, and we press this arrow, we can kind of see how it goes. All right, does it go? So see it's slowly approaching, and you form that cyclic intermediate, and the bromine leaves, okay? So the alkene is supplying electrons to break up that bond. So when you have electrons near electrons, right? What do you think happens to the electrons in the bond? They're going to repulse, get further away, and that bond breaks. So you can kind of think of it that way. Since both these reactants are nonpolar, so it's kind of weird, right? How does a reaction happen? All right, so we get that intermediate. Now what's the next step? We know the bromonium intermediate, not very stable. So what happens next? Yeah, so it's going to attack. Well, from what side do you think it attacks? From the same side as the intermediate, the triangle, or is it from the opposite side? Opposite side, because you can kind of think of like steric hindrance here. The bromine already went away from the bromine. Why would it approach it again? So we press the second arrow. You can kind of see it approaching from the backside attack. And you see how it kind of now rearranges to a trans addition or anti-addition. Okay. And then here, you don't really have to rotate your molecule. So as long as you draw it in the anti-configuration here like this, I don't care. You don't have to like redraw it or anything. Some professors like you to redraw it where the carbon chain is on the plane, but that doesn't really matter to me. Okay? All right. Well, okay. Can we see this picture? No. Can we? Okay. All right. So, but we noticed something about this molecule. If we rotate it, what do we get? We get the cis. And what do we know about this molecule? Is it chiral or achiral? Achiral, right? Do you see the mirror plane here? See that mirror plane mirroring that image right back at us, right? So that's a chiral molecule. So it really depends on what kind of alkene you start with. So we started with the trans alkene, but now if we look at the cis alkene, so the same idea. So here are the arrows you kind of would draw. See right there? See the arrows? Let's see. So one bromine atom is having its arrow. Sorry, I guess that's not very, the contrast is really bad. So one arrow is pointing down, one arrow is pointing up at the bromine, and then this one, the bromine on the bottom here, is breaking. Okay? But if you think about the intermediate here, so we have the cis alkene now, and we do a anti-addition, we now get this situation. Okay? But now if we rotate this, if we try to rotate the bromines together, we actually don't get a mirror plane at all, right? So this one is chiral. So it really depends on what what the starting alkene is and the resulting product of the trans addition. Okay? So this one would be chiral. All right, so this molecule would actually have two enantiomers, but the first one is meso, the trans one is meso. So you wouldn't actually see any stereoisomers. There'd just be one because that molecule is overall achiral. All right, so that's alkene, stereospecific, and the addition causes that because of the intermediate. All right. So let's do some more examples. Are there any questions on that picture? You can access this. It's on Canvas too.
So to say, if you didn't mind just sending the link, but if you have that.
Yeah. Okay. I could point you guys to the link. Yeah. So it's a great way to visualize these things. So remember, alkenes, more variety of reactions. So stereochemistry is actually more important here because there's so many different reactions with different stereochemistry. Okay. All right. Any other questions? Yeah. All right. Okay. So let's do some examples here. All right. So last time we talked about, we actually used the, did I go over the meso example? I don't think so, right? I don't think so. Did we go over this one? So let's do, this is lecture 29. So did we go over this one where the H was on the dash line, but we're working with the trans isomer?
We have
Okay. How about this one? Did we work on this one?
No.
No? Okay.
Yeah,
Okay, got it. Yeah, so this butene. Okay, got it. So this one's going to be the trans butene. The methyl groups are pointing outwards, all right? And just like that example I showed you, if we use Br2, and our solvent is DCM, dichloromethane. All right. So remember, like what I showed you is that one of the products has a mirror plane. So if we attack from the opposite face, it's going to have the same mirror plane. It doesn't matter, right? So this molecule is actually meso. So let's just draw one group that shows this. So let's draw the H, C here. Remember, anti-addition. That's why I draw the bromines in a staggered conformation. All right. So what's going to happen if I rotate this molecule? So I'm going to have my alkene, right? So if I rotate one of these bonds, let's just rotate the right carbon, rotate it 180 degrees. The methyl group now will be pointing outward. And then the hydrogens here. Oh, sorry, it's not a double bond. What am I talking about? Sorry about that. Let's erase that. All right, so the bromines here would be facing, there will be kind of, eclipsing now in this conformation. And then the hydrogens would be pointing on the same side. All right. And like we said before, this has a what? Yes, mirror point of symmetry. So this is meso. So this has chiral centers, but it's achiral because it has a point of symmetry. 2, 3, dibromo. Butane. Okay, are there any questions on that example? All right, so very similar. So you can never go wrong as long as you write the bromines added. They're kind of pointing in opposite directions. That's the anti-addition. So here we get, so let's just summarize anti-addition of Br2. And since you're starting with, it's a planar intermediate, you're going to get racemic mixture. So planar reactant, racemic product. So remember, this isomer wasn't a stereocenter, so we didn't have one enantiomer, so we're not going to get one enantiomer as the product. We're going to get both. Okay, so let's just do another example. Let's draw a chair. More practice with these alkene reactions, okay? So a chair. All right, let's put the tert-butyl group here. And then we're going to put the alkene into the cyclohexane ring. Now, this can work with I2, Cl2, Br2, no F2. So this still works with Cl2 as well. So what kind of products would you predict here? All right, so guys, this is just solvent. Remember, where most chemistry happens in solution, especially for us in the lab, so that we always need a solvent, okay? All right, but how would I draw the product using the chair? Does anyone have any thoughts about that?
So it would have to be
Yeah.
anti to the terpenoid group, right?
Okay. Yeah. Well, one of them will. But the two chlorines added, what would their relationship be? Are they cis to each other or trans or anti?
Between 2 points?
Yeah. So let's draw one chlorine up here, right? Where would the other chlorine be? Down and to the right, correct? Yeah, this, yeah. Yeah. So you'll get this enantiomer, and then you'll get the other one. So it's still considered racemic because you can also get the other enantiomer too. Okay? So plus other stereoisomer. In this case, the other stereoisomer is not going to be an enantiomer because look at this terbutyl group. Wouldn't this be a stereocenter? Right? So this other isomer actually is a diastereomer. Okay, and if you have a different diastereomers, you actually can't predict in what ratio it will be produced in. So you just write plus other diastereomer, okay? All right, so that's another example here. Any double bond, Br2, Cl2, I2, they will give you the haloalkane. So that can be useful just for a variety of reasons. So another important reaction in our toolbox. All right, but does it stop with just halogens or could we mix things up a bit? The answer is yes. Okay. So let's talk about some more instances of this reaction. So I'm going to switch to a new page now. Anyone still writing? Okay, let's see here. I'm going to swipe right a little bit. Okay, so now let's talk about the generality. So this reaction is pretty common, and you could use different reagents here. Okay, number one. So say we have cyclohexene. H2O. All right. So this reaction, the mechanism is pretty much the same, but what happens here, what do you think is going to happen here if we have a solvent that's also nucleophilic? What do you think the product's going to be? Is it still going to be 2 bromines? No. What do you think is going to substitute? Yeah, OH. Good. And that's because usually the solvent is in such high... Remember, let me just go over that. So the product you get is this. All right, so it's racemic, so we will have to mention that it's racemic. So you get the other enantiomer as well. All right, but let's go over, like, why does water attack anyway? Okay. So you pretty much have the same intermediate here. So let's just say it's going to attack bromine right here, okay? All right, remember when we had a charged epoxide? Usually those were kind of like acidic conditions. So even a neutral nucleophile like water can open it, all right? So bromine here is probably not going to be present in a whole lot of excess because it's not the solvent. So water is going to be present all around the solvent, or as the solvent. So water has a more likelihood of encountering the intermediate, and that's why water tends to open the ring up right here. So water here will be coming around. There's lots of water, so water will come around and attack in an anti-fashion, and that's how we get this guy right here, okay? And usually what happens here is that the hydrogen, the extra hydrogen just falls off because remember like an S&1 mechanism, it's very acidic. So I could just draw minus H plus happening right here. Okay, to indicate that the hydrogen is just falling off as the intermediate forms to get to the final product, like that. Yes, Catherine?
Why couldn't the hydrogen bond with the other from?
Oh, the HP, this H plus? Yeah, you could do that too. So let's just draw the intermediate right here. You could do that, but remember bromide, what do we know about bromide? Is it a weak conjugate base or a strong conjugate base? Weak, right? Because what's HBr? What kind of acid is HBr? Strong or weak? Strong, right? So that means Br is very weak. So, but I wouldn't. So I wouldn't take points off for that. Okay. So let me just undo this for a sec. So we get H over here plus. No, Br, you could use Br minus because that's bromide, right? It's being produced. Or you could do water or H2O. Whichever one you do, I don't mind, okay? Because at the end of the day, it's very hard to predict how proton transfers happen. Unless you can see exactly what happens. And we can't do that. Okay, so this gives you the final product. All right, so that final proton transfer, strictly for mechanisms, you should show it. But as for general reactions, you're just trying to map out what happens. Please do that if that helps you understand it better. Okay, that helped me understand it a whole lot. So that's why I did it. Okay. So you see here, we can actually differentiate what happens here. Okay, so you have one there. Okay, so another thing that can happen, let's take our generic cyclohexene again. Now, instead of water, let's add Br2 and chloride ion. So like sodium chloride, if you add sodium chloride in there. Okay. Well, you're going to probably have more chloride in there. If we add a stoichiometric amount, okay, you're going to get the bromine here, and then your chloride ion is actually going to attack here, okay? And that's because you added two different nucleophiles. Well, in most cases here, chloride is probably going to be more negatively charged because it's from a salt, whereas the Br slowly forms from the reaction with Br2. So chloride ion here will substitute instead. And here we have still a racemic mixture. Okay. So it doesn't matter what the other nucleophile is, as long as it's relatively strong and a good nucleophile, it'll still react. Okay. Now, how about we change the solvent to methanol? What do you think is going to happen if we put Br2 and methanol? So very similar to the water example, right? But in this case, what would the nucleophile be instead? Yeah, it's still oxygen. But what else attaches to it? Yeah, the alcohol. So we'll form a ether, right? So now we have the O, CH3 bonded here. So that whole group stays with it. It just doesn't dissociate. So water keeps its hydrogen, OH, and then here we keep the R group, which is CH3, and so this will be racemic. All right. Boom, boom, boom. All right, let's see here. Okay. Now, what do you think what happens if these alkenes are not equally substituted? Which direction do you think it will add? So, for example, let's have an unsubstituted alkene here. All right, so here's ethanol, bromine here. So what do you think happens? Where would the nucleophile add in this case if it's an unsymmetrical alkene? Close. Not exactly. Okay. No, not exactly here. So let's think about the let's just draw the intermediate here. So let's go through the intermediate. So we get bromine, plus right here. Do you remember the epoxide? The epoxide was positively charged. So which side had the more partially positive character? If we think back to epoxides under acidic conditions. So here's a positive charge, right? So which carbon atom of the ring of the epoxide can stabilize a partially positive charge better if we were to partially break this bond? The more substituted one, right? Which one can handle a carbocation better? Just like the epoxide. Yeah, Catherine, what's up? The tertiary side, yes. So this is where ethanol will primarily attack. Oops. All right, let me just erase this partially positive charge here. And then the final product would be, after you lose the hydrogen ion here, okay, you'll get this ether here. And it's also racemic. All right, so it follows Marcon-McCall. Well, it actually eventually follows anti-addition, Marcon-McCall selectivity. So they added to the more substituted side of the alkene. Okay? And then if we use something that's more basic, more negatively charged, it would mimic the trend you saw with epoxides, where it opened the least substituted side. Okay? But that one, don't worry too much about that one. These are really the ones we should be focusing on. Yeah. Okay, are there any questions on that? Does anyone want me to go over the mechanism again? I know it's a lot of steps, but just think how the epoxide opened. It's very similar to that, the rest of the steps. So if you kind of so we have a cyclic, very strained ring, okay, with a positive charge, that will cause the intermediate to be very unstable. Okay. All right. So let's summarize this part by just going over some commonly used nucleophiles, okay? So let me just go to the next page. I'm going to summarize what nucleophiles we use. So for the addition of these halogens and then the opening of the ring, so some commonly used nucleophiles, okay? Let me just write it out. All right, so you can have charged ones, Br minus, Cl minus, cyanide, and then neutral nucleophiles, water, ROH, and RSH. So those are some common ones. So you can get diol ethers, sulfur analogs of alcohols, or ethers, sorry, alcohols, water, and then negative charge ions as well. And then if it's under more basic conditions where you have a negative nucleophile, think epoxide, open, least hindered side, okay? And things that are weaker nucleophiles, neutral, they'll mimic acidic conditions. So I think that also will open up on the more substitute side, okay? Yeah, I think that's what would happen, yes. Yeah, so we'll focus on that, okay? All right, so let's just summarize. The one with water. Okay. So we call this the formation of a halohydrin. All right. So halohydrin, you added halogen and water to the double bond. So that's why we call it formation of halohydrin. All right. All right. So mechanism, very similar to just with bromine, except water is your nucleophile now. And it adds in a trans fashion. So the problem with this reaction is that you get competition. So it's not fully just the halohydrin forming. You actually get competition from the dibromo. So halohydrin. So this is a halohydrin, has a halogen and an alcohol, racemic. And you also get, so bromine is also going to compete with water. So that's why you get some of this too. So this is a minor product. And since this is in the chiral center, so that it's not racemic. So that's why I didn't write racemic. Okay. All right, so the key takeaways here is that you can functionalize alkenes with halogens and water, both in a single step, okay? Because you could difunctionalize it from just a single functional group. So that's pretty neat. All right, so but the thing about here is that if you have an unsubstituted alkene, you want to just go with the more substituted side based on the opening of the ring I showed you. Okay? All right. Okay. Any questions about halohydrins? No? All right. So why are these useful? Why are these intermediates particularly useful? All right? So I'll highlight a few things of this reaction because who knows? You might see it. today. All right. Anyway, useful intermediates. In making epoxides. So in general, these intermediates can be useful to make epoxides or any ring structure, like a cyclic ether, okay? All right, so let's practice predicting the product. Well, no, when I said that, right, I didn't mean like the alkene reaction, okay? I meant like one of these other steps. So we have 0 degrees Celsius. All right, so what would the product of this first step be? Sorry, guys, can you see that? Chlorine, water, 0 degrees Celsius with an alkene. So what would the product look like? We're going to break the double bond. And what kind of functional groups are we going to form? And? All right, I heard chlorine. It was alcohol? Yes, good. So the beauty of this, any isomer you get, the relationship of the alcohol and chlorine, are they going to be on the same side or opposite sides? Opposite sides, good. All right, so you get some pretty decent yield, 73%. Pretty good. Okay, now this is what I was talking about. We learned about reaction with alcohols and ethers, right? So kind of relevant today for exam hour that's coming up. All right. So let's do sodium hydroxide, water at 25 degrees Celsius. All right. What do you think is going to happen here? So you have two kind of options here. Does anyone want to take a guess, like what maybe the product would be? Well, I know I wrote epoxides, but what would you think if I didn't write that? What would you think?
I would think the sodium hydroxide, the hydroxide would make the alcohol.
Okay, good. That's what I was expecting. Well, remember, acid-base reactions, if an acid-base reaction can happen, that's much faster than nucleophilic substitution. All right, so that's why this one will, so I'll write the steps here for you. What will happen first is that the hydroxide, right, will take this H and then put that electrons back onto the oxygen. So now we form a good what? Close, not leaving group. Yes, a better nucleophile, right? And do you guys remember what I said about intramolecular reactions? Which ones are faster, intramolecular or intermolecular? Intra, because the leaving group and the nucleophile are just right there, very close by, okay? Intermolecular is when you have two molecules approach each other, and that has difficulties, Brownian motion with the molecules moving randomly, and then you have to get them the right orientation for SN2, and it's a secondary substrate, so it might not work as you predict, but there's no way that an intramolecular reaction can auto-deprotonate itself to form an alkene. That's the geometry of that is just impossible. So this will always go to an intramolecular ring closure. Like that. And see, the oxygen is coming from the top face, so the epoxide formed will be from the top face. And of course, you can form the other enantiomer as well. But what's wrong with this? If you think about this, isn't the molecule meso? Yeah, so there's only one isomer, or one structure. And you get this in pretty good yield, 70%. So that's how you make ethers, epoxides, intramolecular Williamson ether synthesis. All right. Are any questions about that intramolecular ring closure? So the ring closures are cool just because they form these nice rings, and that's how you sometimes that's how you make big ring structures in like natural products. Okay. So that was epoxides. So now there's an even better way to make epoxides. You don't have to start from the alcohol, the halohydrin. You can just make it directly from an alkene, okay? So let's look at that reaction next. So reaction number 8, epoxidation of alkenes. Okay, so let's go over here. All right. So I might not have time to show you exactly like the visuals of epoxidation, but if you're interested, that website we looked at earlier has a great way to visualize this, okay? So I will forward you that website. All right, so reaction number 8 with alkenes, epoxidation. So how we do this is peroxy carboxylic acids. So peroxy acids are very reactive forms of carboxylic acids, and they have very different chemistry, and they're very unstable. So they're not well known. Well, they're well known, but they're not stable molecules. So they're not used as solvents. All right. So the way we do this is we use something called MCPBA. MCPBA. All right, that's a mouthful. And then here is the solvent core form. So MCPBA stands for meta-chloroperoxybenzoic acid. So here, meta means your chlorine is in the 3rd position, and your acid group is it automatically gets the 1 position because of the carboxylic, the carbonyl. And this is it's like a hydrogen peroxide reacted with acetic acid. That's called a peroxy acid. All right, so that's called meta-chloroperoxy benzoic acid. So benzoic acid is when your R group on a carboxylic acid is a benzene ring of some sort. And meta means the 3rd position away from the first attachment to the acid. All right, so meta means the 3rd position. So 1, 2, 3. But don't worry about that. We haven't talked about these indicators for locations here. That's 18B. All right, so what product do we get? Well, we get a racemic mixture. Well, this is achiral, but we get epoxidation right here. Straight up, just like that. And it's pretty straightforward. You just mix these chemicals at like 25 degrees Celsius, and you stir it for about an hour, and you got the epoxide. So it's a very useful reaction. All right. But now the question is, how does it work? So the mechanism is complex. So it's a lot of arrows all at once. So to really practice this, you got to kind of practice drawing it a lot, okay? But let me go over the mechanism. All right. So let's draw our alkene. All right, so I want you to line up the peroxy acid like this, because this oxygen right here is the electrophilic, or the most reactive one. Okay. So let's write the oxygen right there. All right, and this R group could be anything. I'm not going to write the benzoic acid. I'm just going to label it as R, okay? All right. So this oxygen right here, so see this oxygen right here? That oxygen is next to another oxygen. And that oxygen is next to another carbonyl group. So what do you think this oxygen, this last oxygen right here with the OH, you think it's going to be electron rich or electron poor? Poor, good. So what we can say here is that this is partially positive. Okay? Well, alkenes has electrons attracted to partially positive things. So this is a rare instance where oxygen is actually attacked. Okay? So let's follow these arrows. So you're going to form a bond here to this oxygen. Sorry, let me just draw like that. Okay? Now this bond is going to break and form another bond, a new bond. So there's two bonds of oxygen now for the epoxide. And then what happens here? This bond breaks. And then this bond right here is going to grab this hydrogen. So it kind of looks like a circus show of electrons moving around. And what you get is the epoxide. So let's follow these arrows. So what's happening to my oxygen that I labeled with positive charge? Where is it going? Yes, becoming part of the ring. Good. Now, the other oxygen, the one that the OO bond broke, right? That's going to go to the acid. The acid is going to, from the other oxygen, pick up an H. And that's going to be my carboxylic acid group. So R, double bond O, OH. So this OH is from this group. And this O now, oh my God, sorry. This O is from this one. So you see they kind of swap places in the double bond. Okay. So, well, the alkene is attacking this oxygen. You would think the more substituted alkene, the more electron rich, right? So would you think that would be a faster reaction if we had a more electron rich alkene? All right, let's talk about that. So, let's talk about relative rates of oxa, cyclopropane formation. All right, so this is epoxidation. All right, so if you just have ethene, all right, this rate is 1. So that's going to be less than a primary, or sorry, a monosubstituted alkene. Okay. CH2, and here's just H. This rate is 24. So it's 24 times as fast. So you can see here, if we have more alkyl groups, the alkene gets more reactive because you're donating electrons to more of the double bond, and that gives you more reactivity. Now, this is even more pronounced when we have a disubstituted alkene. So the trans one. All right, so this rate is 500. So way bigger, way larger too. Oh, I did not move it. Cool, okay. And then this is kind of similar to the cis version here. Or when they're, no, sorry, not the cis version. When they're bonded on the same carbon atom. So in my notes, I don't really have an example where it's cis, but I think it's relatively the same as this one. So 500. All right. And then this is less reactive than a tertiary one. Or a tri-substitute, sorry. So you see the rate, it's kind of increasing exponentially here. So 6,500, very fast. So this reacts very fast, okay? And then this is even less reactive than a tetrasubstituted alkene. Which reacts very fast. So this reacts the fastest. So it's much greater than 6,500. It's so fast, maybe it's too fast, we can't actually record the rate. All right, so an application of this is, say you have two double bonds, but you only have 1 mole of your per acid. Which double bond does it preferentially epoxidize first? All right, so let me show you an example of why we do this. All right, so here's my solvent, chloroform, 10 degrees Celsius. So you got to do this at low temp, because if you don't, the per acid may go off. It may just decompose. All right, so here's my per acid. So this is called per acetic acid. So it's like MCPBA, but you have a methyl group instead for the R group. All right, so here I'll put 1 equivalent. All right, so based on what we know about the trend in reactivity here, which position would get the epoxide preferentially? Which one? Oh, this one?
Yeah.
All right. Anyone else has a guess? So which one reacts the fastest? Is it the primary alkene? Sorry, this kind of alkene right here? Or is it the di-substituted one? Something like this. We're going to go for the one on the left. All right, and we'll explain that right here, okay? So what you get is the epoxide forming preferentially on the cyclohexane ring because it's di-substituted. Okay, right here. So you get this in 86%, so a pretty good reaction. Pretty straightforward. So here we can see that we only form the epoxide at more electron-rich alkene. Okay? So we have 2 positions here, right? So this will be considered a mono-substituted alkene. What about this one? What kind of alkene is this? What substitution pattern? Mono, di, tri, tetra? Yeah, di-substituted. Okay. All right, but if we have an excess of the peracid, we would just epoxidize everything. Okay? And if you looked ahead, I think that's one of my examples in my 4th practice exam, where we just epoxide that whole big ring structure. But if only one, look at the most electron-rich alkene, more alkyl groups, okay? All right, so what's the point of forming epoxides? Well, we can open them, right? All right, are there any questions on this mechanism? So let's just put a star here. Possibly one of them you have to know on the final, but I won't comment on which one, okay? Possibly. One alkene one, okay? And maybe one old one. Okay, any questions about epoxidation? No? Okay. let's move on. So why is this important? Okay, so let's talk about this one. Oh, this is better. No, I don't want that. All right, better. All right, synthesis. So this is important for synthesis of anti-vicinal diols. All right. Does anyone know what vicinal means in terms of, I don't know, I guess just in general? Like you're in the vicinity of someone else. All right. So let's take trans 2-butene, like before. So let's take trans 2-butene. Okay. So one, we're going to use MCPBA. Okay, and two, we're going to use H plus and H2O. So what does the first step do? What kind of functional group do you form there? Oh, sorry, I forgot the solvent. Anyone? So when we use MCPBA with an alkene, what's the functional group that forms? It's the epoxide. Good. So we form the epoxide, and then what happens when we subject that to acid and water? Yes, to form alcohol. So you're going to get the diol. Okay. So this comes out to be the diol, the trans diol. Okay. So we call this vicinal diol because the alcohols are on adjacent carbon atoms. So that's called vicinal diol. There's another term we write called geminal diol. That's when it's attached to the same carbon atom. But this is vicinal, okay? Okay. But remember, like trans-butene, we have trans addition of the same group, like those trans-bromo. So this becomes meso. So this is meso 2,3 butane. And how many alcohols do we have? 2. So what's the name, the ending? Diol. Thank you. Good. Now, what do you think will happen if we use the cis isomer? Let's draw the cis isomer. So do you think we're going to get just one molecule, or are we going to get a mixture of stereoisomers? Yeah, because unlike this one, remember the cis example we did before? It did give us a symmetrical dibromo compound. So we're going to get something very different. So here we're going to get trans diols, but we get actually 2 different ones. Okay? So you're going to get enantiomers here. All right. So first we get the RR enantiomer. So 2R 3R, 3 butane diol. All right. But what's the other one? What other isomer do we get? So we get the other enantiomer, right? Which isomer would that be? RR, SS? Yeah, SS. Good. So you see here, when we try to rotate one of these bonds and its groups, we won't get a meso compound. So this is SS. So 2S, 3S, 2,3 butane diol. All right, so we get an equal amount of these enantiomers. So we get a racemic mixture. Just stick with me. There's a lot of reactions, I know. Is anyone utilizing that flashcard website? It might help. Or flashcards in general. I don't recommend flashcards, but I understand why we use them. Okay. Are there any questions? So this is trans diol, anti-vicinal diol. Wouldn't it be nice, though, if we could get syn diols where they're on the same side? Well, we can. So that's our next reaction. Okay, so that was number 8. Now let's go to number 9. So now we have synthesis of syn diols. All right. So, in order to do syn diols, we need a different reagent. Osmium tetroxide. You might not have heard that element before. Osmium, OS. Okay. Osmium is very expensive and it's very toxic, so we try not to use it. If we have to, we try to do this reaction catalytically, okay, or find different reagents here. So you need both osmium and then you need a reducing agent like dimethyl H2S, sorry, not HS, H2S, or sodium bisulfite. Like that. All right, so what do you get? You get syn diols. So let's write the equation here. So you get syn diols. The OH groups are on the same side, so that's a syn relationship. All right, so the mechanism here, similar to the MCPBA, but not quite. All right, you have your alkene. So if it adds to the same side, what do you think has to happen? Do you guys have any ideas, like what has to happen here? So we would think about 2 of these oxygen atoms, right? They have to add to the same side of what? So the same side of the alkene, right? In order to get those OH groups on the same side. So what happens here is that the double bond is going to attack one of these oxygens. This is going to go back to osmium. And this pushes these electrons to form a bond with the oxygen atom. So now you're going to kind of have this complex. And so what happens is you draw the resulting intermediate. And what happens is that both oxygens add to the same phase. And osmium has gained 2 more electrons, so that's why now its oxidation state has went from 8 to 6 right here. Like that. Okay. And then the second step is reduction. You're going to cleave those oxygen bonds with H2S or sodium bisulfite. Okay, so that's going to cleave those bonds. You don't have to know the mechanism. I think the mechanism, I haven't found one, so I think it's unclear. So what happens here is that you're going to cleave these bonds and add pretty much an H to the oxygen. So you cleave those bonds and generate the syn diol as your intermediate. So I think what happens is that the electrons go back to the osmium and you get a form of osmium that's reduced. But the bad part about that is osmium is not recycled, so it can't do this chemistry again. So that's why you need, there's other ways to do this reaction without sacrificing the osmium. So they learned to do it catalytically, that regenerates the reactive form of osmium tetroxide. So that's the mechanism. Okay. So there's another reagent we can use, a much more safer one, but it's much more reactive. It's potassium permanganate. And we weren't able to do this test in lab, but next semester we'll be able to. All right, so the takeaway here, osmium, syn diol instead of trans diol. Okay. Are there any questions on the mechanism? So we got to add the 2 oxygens to the same phase, so that's why it proceeds in a circular fashion. So it's concerted. Okay, so that's osmium tetroxide. I think there's some problems on the homework, but don't worry, the homework's not due until like December. But please get started. Okay, let's try a new one. Let's do potassium permanganate now. The potassium permanganate test. Permanganate. Yeah, potassium permanganate is so ubiquitous. You can even buy it on Amazon because apparently it's on the WHO's list for essential medicines. It's a very ubiquitous chemical. All right. So permanganate was used historically to detect unsaturation, so double bond character in a molecule. Okay, so how this works is potassium permanganate, all right, reacts with KMnO4. You guys remember what color potassium permanganate is? You might have done this in 1B. It's a very beautiful color. It's like what? Like purple? Pink? Okay. Dark purple. It looks really nice. So dark purple. It looks like iodine sometimes. The color of iodine. So you have to do this cold, because if you don't do it cold, it can cleave a carbon-carbon bond between diols. So you have to do it cold, okay? So the mechanism is very similar to osmium, okay? And then instead of, a reducing agent, it just hydrolyzes with water to form manganese dioxide, all right? So another technique here to form manganese. All right. And then the driving force here is the formation of the brown precipitate, manganese dioxide. So it's a brown in color. Not very pretty to look at, but it's still, it's a result of this process, okay? So that's permanganate. So the problem with permanganate is not very useful is because it is too reactive with other functional groups, all right? So let me just put this caveat. Reaction is not useful for synthesis because of over-oxidation of diols. Okay. So what happens here, potassium permanganate, if in water, and if you heat it up, okay, it tends to cleave the bond completely. So what you get here is cleavage of the bond, cleavage of the ring, and you get oxidation of the alcohol to carboxylic acid. So this is a great way to form diacids. 1, 2, 3, 4, 5, 6. 1, 2, 3. Whoops. 1, 2, 3, 4, 5, 6. Oops, I think I did too many. So you get cleavage of that bond, you get a diacid. Just crazy. Okay, so that was, I think we did that as reaction 9, right? Synthesis of syndiol. So potassium permanganate, so if you're cold enough, that's okay. But it's not very useful. But for our purposes, if you put that, that'll be okay. All right, since I taught you this way to do it. But this is usually just used to determine if your molecule has a double bond in it. If you have a positive permanganate test, that means you have a CC double bond. Okay. All right. Are there any questions about synthiols? So, like transdiols, we can actually get the syn version of it. And it has to do with the fact that the metal osmium coordinates to the same face of the double bond, just like we saw with hydrogenation. Remember hydrogenation with palladium? Attack the same face of the double bond. All right. All right, reaction 10. All right, this one's cool. Addition of carbenes. All right, so a carbene is a reactive form of carbon, okay? So this gives us access to the synthesis of cyclopropanes. So synthesis of cyclopropanes. All right, so what is a carbene? So this is a carbene. So it's a unfilled octet of carbon. So this is CH2. It's not a radical. It's a neutral intermediate of carbon without 4 bonds. So it's a CH2 reactive species. Okay? Very reactive. All right. So how do we generate carbenes? Well, to generate them, that's very difficult to do because it's so reactive. So one way to do it is you have diazomethane, so CH2. So diazomethane, you have this N2 group here. That's diazomethane. So just by looking at it, you can kind of think, okay, this should be really unstable. It is. It's shock sensitive. If you drop it, you get a speck of dust on it, it will explode. Okay? So that's why we don't handle it anymore. And when people handle it in the lab, I ran away. Okay? It's so explosive. So this is called diazomethane. Okay? But we can have a resonance structure here. So sorry, I should draw all the electrons. All right, negative charge right here. So what can happen is you can have this resin structure, and now you put the negative charge onto nitrogen. And we get this resin structure right here. All right, so we should know something about nitrogen. That is the world's best leaving group, the most stable molecule. So if you can generate nitrogen, it will leave like that. All right, so this is the world's best leaving group. So what happens here is that this will leave as nitrogen gas, okay? So if you just heat this or have copper and heat, this will cause this reaction to release nitrogen gas, and you will form a carbene, like that, okay? And the thing about the carbene is that it's planar, like here, planar, and the lone pair is in an sp2 hybridized orbital. And if we draw the p orbital here, the p orbital is empty. So empty p orbital right here. So that's an sp2 hybridized orbital, and it's empty. So this explains a lot of its reactivity with alkenes, okay? So here, you don't have to worry about how a carbene forms, but you should know that it generates this reactive intermediate, and then it can insert into a double bond. So let's talk about that next. How do we go to a cyclopropane? All right, so I actually did this reaction, not with diols and methane, but a different reagent, and we'll talk about that in a bit. But what happens here is you can synthesize cyclopropanes pretty easily. And I was trying to synthesize a cyclopropane to test the mechanism. And it caused me a lot of problems because I couldn't synthesize it a particular way. So I had to it set me back a bit. So sometimes these reactions, they don't always work out. All right, so let's have our cis alkene. So you notice here that the alkene adds on the same side of the double bond. So it's a syn addition, okay? So you kind of maintain the stereochemistry here. So we could take diazomethane, CH2, N2, light, and then copper, metal, and you'll get a triangle cyclopropane, and our groups are going to be on the same side. All right. But let's talk about the mechanism. How does this work? All right, so the R group. All right, so what happens here is so remember when I drew that carbene structure? It had an empty p orbital. So your carbene can attack the alkene, and the alkene can donate its electrons into the empty p orbital, and that's how the other bond forms, okay? So this bond will enter here, and then this will go to this carbon, and then you will get your cyclopropane. R prime. So that's how we form the cyclopropane. Okay. So are any questions about those arrows? So these arrows, they look very similar to the reaction we've gone over, right? Alkene attacks one atom, lone pair on the group that's being attacked, attacks the alkene. We form like a bridge or some intermediate there, or it's cleaved into separate groups, right, eventually. So there's a trend you can kind of see here. All right. So there's a few more reactions I want to cover before the end of today. So just stick with me, okay? So, well, there's another type of carbines, okay, we'll talk about. And we'll talk about the safe one that we can use. And then we're going to talk about ozone. Okay? So, well, we can also talk about, let me see, what do I want to see here? Dichlorocarbene, okay. So now we can have dichlorocarbene from chloroform. Okay. So let's talk about the mechanism right now. All right. So how this works is you have potassium tert-butoxide. Okay. So that's reacting with chloroform. All right. So we look at chloroform, right? What can we say about that H? If we react with the base, what can we say about that H? Is it acidic or not very acidic? Very acidic. Okay, so you can actually deprotonate chloroform, so that's why you can't mix chloroform and base. It's unstable. So potassium tert-butoxide here will deprotonate that and put the electrons on carbon, but it's particularly stable because carbon atoms, when they're next to electronegative atoms, they can actually give you stable carbon anions. All right. So this structure is not very stable. The double bond, that lone pair there, will actually cause one of these chlorines to eject, like that. This is called alpha elimination. So remember when we talked about E2? Remember E2? This group right here. So this is the alpha position. Okay. This is the beta position. This is called beta elimination. The hydrogen is removed from one carbon over, you form a double bond. Can you form a double bond in alpha elimination? Probably not, right? You would have to eject some electrons from chlorine, so no. So this is alpha elimination, okay? So what you get here is the chlorocarbene, dichlorocarbene, CCl2, like that. Now, like a carbene like this, instead of two hydrogen atoms, you have two chlorine atoms. So that might be useful for synthesis, okay? So I'll show you an example of how they use this, okay? So here's my example to you all. All right. All right, potassium tert-butoxide. And then this is a solvent, tert-butanol. It won't react, so it's all right. So this also works with CHBr3 as well. So let's just put an asterisk there. It also works with the dibromo compound, okay? All right, so you get this reaction, and the product you will get is a cyclopropane. But you have two chlorine atoms on there, so that might be useful. All right. So while you're doing a carbene, do you think the mechanism is any different? So it doesn't matter if the carbene has hydrogen or chlorine, sorry. So So how will the arrows work? So the lone pair attack the carbene, right? And then the double bond attacks the carbon, right? The p orbital of the carbene. So you also have a p orbital here. So that's where it's attacking. See the p orbital? Empty p orbital, it attacks that carbene. So you can form 2 bonds. All right. So what happens here is you get the carbene. And you could represent this by pointing it upwards. So it goes, the stereochemistry of the double bond is maintained, and it adds syn addition to the alkene. So that's how you form a cyclopropane. And cyclopropanes are actually prevalent in nature. So you kind of see this all the time. There's cyclopropanes, even though they're very strained, they have some relevance in terms of the natural products we can get. All right. I know it's a lot, okay? Next week we'll check back on Tuesday, okay? Because after this, it's just going to be review, okay? So come to office hours and come to lecture. We'll do a review. Maybe I'll make a new handout, in addition to the ones I sent out, okay? So you can kind of have like a booster pack to prepare for final. All right, so now I want to talk about the reaction that I did. Okay, that I tried to do several times to form a cyclopropane. It's called Simmons-Smith reaction. All right, so this is the third way to make a cyclopropane, Simmons-Smith, and for sure it's the safest. All right, so it's an organometallic reaction. I know it sounds like some waxsmith, but that's not the case. All right, so the reaction only works with diiodomethane, so it looks like dichloromethane, and then you have to use something called a zinc-copper couple. So it's a solid mixture of zinc and copper melded together. So zinc, copper couple, so that's a reagent, that's the catalyst, and a doxide. All right, and the beauty of this is that the stereochemistry is maintained. So you have a down alkene here and a wedged alkene right here. So that's the alkene you have. Okay, sorry, not alkene, cyclopropane. All right. So the mechanism has been well understood, and it's going through something called a carbenoid. So a carbenoid is when you have a carbene that's kind of chemically bonded to a metal, okay? So a carbenoid. So what happens first is your diiodomethane will insert into the zinc-copper couple. So remember when we did, what happened? Remember when we added magnesium instead? What inserted between the carbon-halogen bond? Ooh, Grignard. Magnesium. So in this case, we're just using zinc-copper, okay? But what happens here, the zinc-copper couple, what you get is insertion of only the zinc. So the copper kind of is a mediator, okay? It kind of helps the zinc insert. So zinc is also a common metal that's used in organic chemistry for these type of reactions. And then here, the other iodine stays in place. So this is called a carbenoid. So I will say here, it's like a carbene. Okay? All right, so the mechanism has been well documented. There might be a mechanism on that website, but I found this mechanism actually online. Okay, but what happens here is that it's like the carbene reaction. You have the alkene here. Okay, so let's just draw the carbenoid like this. Okay, so I'm going to draw the iodine right here. the two hydrogens coming out of the plane right here, or, you know, kind of to the side there. And then my zinc group here is going like this. All right. So think of this carbon atom as a carbene. It's going to insert. Okay. So what happens is this is going to attack the carbon atom. This iodine is going to go to the zinc, and then this bond here is going to come down and attack the carbene, the alkene. So what does this look like in the transition state is you're going to draw this structure here. So let's see if I can draw this. All right. So you're breaking that bond. And the R groups are still trans to each other. So see here, the carbenoid kind of traps the alkene in place so it can add to the same face. So what happens here is you're forming bonds to this carbon of the carbenoid. And the zinc bond is breaking, so you're breaking the zinc bond. Okay, and that bond is forming to iodine here that came off the carbon atom. Okay, so this is the transition state. So you don't have to reproduce this transition state, okay? You don't even have to reproduce this mechanism. You just have to know the end product. And what we get is our cyclopropane. So this reaction works the best in, So this reaction works the best if you have no other functional groups. So what I tried to do, I had an alcohol on my molecule, so I guess it didn't tolerate that. So the reaction barely worked. I got like 25% yield. All right, so not the best. So I had to find another way to make what I wanted. So not a good story to tell, but that's what happens in research. Okay, so that's cyclopropane. So what's our common theme here? The reactive intermediate is what? This carbenoid, right? So what's a carbenoid or carbene? It's a carbon atom that has a lone pair of electrons instead of a fourth bond. So that makes it particularly reactive. Okay? All right. Well, I guess I won't have time to get into the other stuff I want to talk about, but we can talk about one more, and that's ozonolysis. Okay? I want to talk about coupling reactions, but that'll have to wait. We won't talk about that. It's just something cool. Okay. So that's carbenes, carbenoids. Any last questions before I talk about the last reaction of alkenes, ozonolysis? Okay. All right. So this mechanism, if I had to rank all these mechanisms, there's a reason I presented this one last, and because it's the hardest. And I most likely will never ever have you reproduce it. But it's interesting to know how it works because ozone is particularly reactive. You know why? If you have ozone, too much ozone, it kills life. So that's why it's a powerful oxidizing agent. So the penultimate reaction, ozonolysis. Very useful reaction though. So oxidative, cleavage. All right. Does anyone know the formula for ozone? It's similar to oxygen, but has one more what? Yeah, O3, so ozone. All right, so to generate ozone, you need an ozonizer. So that's where you kind of take two oxygen atoms, and you hit it, and you form ozone, and they combine there. Okay, so one is using ozone. The other is a reduction step with zinc and acetic acid. And look what you get. You actually cleave the molecules, and you get carbonyls out of them. So you're adding oxygen across two double bonds, and then you're oxidizing that. It's like you have two alcohols on adjacent carbon atoms, and you're oxidizing both at once, and you cleave the bond at once. So this could be useful if you need to get to a particular structure, but then you can also create a lot of waste if you have one carbonyl that you don't need. So not very atom economical, so not very green chemistry here, but still it's very useful. All right, so what is this useful for? Aldehydes from alkenes and ketones. All right, so let's do an example. So here's my aldehyde. All right, ozone, dichloromethane, and then 2, we can either use zinc and acetic acid, or you can just use dimethyl sulfide. So we see dimethyl sulfide again, or a sulfide reagent. That's a good reducer. They're good reducing agents. They just like oxygen. Okay, oxygen. Sorry. So here you see so this one comes from this group. See that group, 2 methyl groups there. So that becomes an oxygen atom, and then you get the oxygen atom with the aldehyde right here, and that came from right here. So you kind of look at those 2 carbons, separate the bond, keep the double bond, replace the atom it lost with oxygen. So that's ozonolysis. All right, so that's ozonolysis. So all you really want to be able to do here is recognize what product can be made. All right, cleave the double bond, form 2 carbonyl compounds. That's it. When I was doing this reaction, I tried to remember the mechanism. Didn't happen. Okay, so the mechanism is a little complex, but I'll show you how it works, so we can kind of get an idea, like exactly like how does this magic happen, or so-called magic. Okay, is there any questions about the products here? So ozonolysis, oxidative cleavage. You're oxidizing carbon, but you're also cleaving the central bond. All right, so let me just. Oh man, I don't have batteries. I think I'll be fine though. Okay, the mechanism. How does it all work? All right, there's a few steps. So we'll use the remaining time to go over a few steps, okay? Step 1, oxidation. All right, so this has 2 parts. We're going to first form part A. So this is something called a molozonide. All right. All right. So ozone looks like this. So ozone has 3 oxygen atoms bonded together. And then one oxygen atom has a negative formal charge, and the other one has a positive formal charge. So it can actually accept and donate electrons. So we can do something like this and do something like this. And then this double bond comes back up to the oxygen. Okay, so this forms an intermediate that is very unstable called a molozonide. I'm probably saying it wrong. All right, so this is important in like atmospheric type chemistry where ozone could maybe be present. Because oxygen, two oxygen molecules get hit with UV light. Ozone in the atmosphere, okay? Sorry, not two oxygen molecules. Ozone captures that UV radiation and produces oxygen. So why do you think ozone up there is so important? It protects us from UV radiation or solar rays from the galaxies and the sun, all right? So we need ozone in the upper stratosphere, etc. Okay, so that's the purpose of ozone. All right, so if you see something with three oxygen atoms, you can think, okay, well, that's not going to last very long. It's going to decompose, try to release oxygen. And that's exactly what it does. So it forms this. Okay? So, a lot going on there. So what it's doing is, it's fragmenting. Okay, so it's almost impossible to reproduce this mechanism unless you practice it a lot. So there's really no kind of flow or kind of rationale behind it. So it's kind of bizarre. Okay, so let's draw the result of these two products. We get acetone. So that's one of the carbonyls. And then we get something called a carbonyl oxide. So it's a positively charged oxygen bond right here. So this is called a carbonyl oxide. Okay. So you might think, okay, we're done. There's the other double bond in the carbonyl oxide, so that oxygen atom might just have to go somewhere. Not the case, unfortunately. So now we have part B. Ozonide. So it actually comes back and forms a different compound called an ozonide formation and reduction. Okay, so we're going to go over those two steps. All right, so let's line up our acetone molecule. And then we're going to line up the ozonide. Sorry, the carbonyl oxide. We're going to line that up first. Boom. All right, so here's my carbon atom. All right, so it's going to line up again and then rearrange once more. So this will attack this carbon, partially positive. This will attack this carbon from the oxygen, and then this will go up right here. And now we form a different cyclic ring called a ozonide. And the only difference is the oxygen atoms are in different seating order here. So now it's 1, 2, and 3. Sorry, 1, 3, and 4 in the ring. That's called an ozonide. Okay, so it rearranges to this weird ring structure again. All right. So this is how it works. My recommendation is to don't worry about too much about this mechanism. Just worry about the end product, and that it's a tool to give you cleavage of the alkene. They give you double bonded O molecules. Okay. All right. So that's the ozonide. There's probably a lot going on, but any questions about this rearrangement here? Okay. I know it's a lot. Now the final step. What's step 2? Reduction. So I'm going to show you reduction of the ozonide with dimethyl sulfide. All right. All right. Okay. So the proper mechanism, I'll show you what the mechanism looks like. Dimethyl sulfide right here actually attacks one of these oxygens, and that causes the whole thing to fall down. Okay. So what happens here is this will attack this oxygen. This bond will attack this oxygen, this sulfur. All right. And this will break into here. This will break into here. And you see here, now the two double bonds form, and we get DMSO. All right, that's the mechanism. Does anyone want to reproduce that? No? Okay. I felt the same way when I learned it. All right. So one thing I want to show you, though, is just do one example with the time we have left, okay? Because we know what happens when it's just a linear alkene, but we have to know what happens when it's a ring, okay? So let's use that example I did before with cyclohexene. So let's just go to a new page. So here's my new page here. Here's my example. Remember we did this? Permanganate. Remember we said it gives us acids here? Okay, so it broke the ring, right? Ozone does the same thing. Okay, so we can have this ring, but it's actually less milder than permanganate, so it won't go all the way. So two here you'll have, let's just use dimethyl sulfide. So you're going to break this ring here. Okay, so we're going to have a similar, so let's just make this the 2 points on this carbon. So 2 points right here. So we have a point there. So 1, 2, 3, 4, 5, 6. All right, we cleave the double bond. What kind of groups do we add to those carbons? If it's ozonolysis. Double bonded O's. So there's actually H's here, right? Look at the H's here. So let's add double bonded O, H. So the beauty of ozonolysis that it stops at the carbonyl, does not oxidize to the acid. Okay. The last two examples I had, it was just like identifying unsaturation, but we don't need to know that. So, all right, that's alkenes. That's all we will cover. All right. See you guys over there. We'll start a little bit after 3, so don't worry. If you need to get a little something to eat, pick me up. Go ahead and do that.